and thanks everybody for joining. So yeah, so the subject of the talk is related to exponential fitting, and I mean, there are many kind of possibilities to define the problem, and this is really a huge topic with many applications. So today I will be talking only about two applications that I was personally have been involved in, but really, I mean, and I don't touch a lot of aspects of this very fascinating subject. So what is basically exponential fitting? We are given some sequence, this m sub k, and we would like to represent it as as a linear combination of exponential functions. And here it's basically the zj's call them nodes or exponents. And the alpha j's are some amplitudes, so both of these variables are unknown, and there is some perturbation, which at this point I don't specify. So given some noisy data, we would like to recover the parameters of this sum. So yeah, so I've already here I've made some assumptions, such as for example the number of terms in this sum is fixed. It is given to us, which is frequently not the case, but I'm kind of skipping all that and just focusing on the basic problem at hand. So yeah, so we assume that there is some ground truth, and we would like to recover this ground truth. The question is how well can we recover? Yeah, how close can we get to this ground truth? So this is somehow the basic setting. Again, some may think that maybe I throw the baby with the water here, yeah, and don't consider very important questions. But again, that's the setting that I'll be talking about. And really, I'm not able to cite all the and even to mention all the huge literature on the subject. So I've listed some of the names of the authors that have very relevant works to this topic, and really apologize that if I missed somebody. Yeah, so what is my plan for the talk? So I'll introduce in some more detail how can we solve this problem. Then I'll talk about the application of this problem to the question of super resolution, which is recovery of sparse Dirac measures from band limited and noisy data. This is also a topic of substantial interest recently. And then I'll talk about some new application that we started to look at, which is related to inverse problem in reaction diffusion equations of parameter identification. And I'll discuss how exponential fitting can be applied to this problem with some guarantees. So that's the plan. Okay. So exponential fitting, yeah. I mean, again, one can look at this problem from many perspectives. I like to think about this as a kind of a parametric algebraic problem. And in this respect, actually, the sum of exponentials is not the most, let's say, general model that one can deal with using these algebraic tools that I will discuss. So one can, for example, replace this constant coefficients, this alpha j's by some structured functions, for example, polynomials of fixed degree. And they ask the same kind of question: how can we recover these nonlinear parameters and these linear parameters from noisy data? And the fundamental kind of observation here in all this business that there is some algebraic relation between the measurements. So if we take this sequence, let's say without noise, yeah, just the noiseless measurements, so there will be some algebraic relations between the measurements, and in particular there will be some recurrence relation, linear recurrence relation, which is satisfied by this measurement. So the most simple case you can think about is, let's say we have just one term here. So the A and the Z are unknown, and in this case, it's immediate to see that there is a recurrence relation of order 2, which are satisfied by every consecutive pair. And from that, we can recover, if we have noiseless data, we can recover, in this case, this nonlinear parameter, yeah, but just dividing, and then we can plug it back and recover the linear parameter. So this is the most simple case. If you are bored with the talk, so you can think about what happens, yeah, with and of course, if you don't know the answer, you can think about what happens with, let's say, 2 terms or 3 terms. What kind of recurrence relation do we get? And I will come to this later. So given this recurrence relation, we can recover the parameters by explicit algebraic methods, and then the question becomes, okay, what happens when you have noisy data? That's the whole issue here. How stable are the methods that we develop, or the problem itself, to perturbations in this data? And the second important question is how to once we know to quantify the stability, can we attain the stability by some actual algorithm that we can implement? So in the most general setting, this kind of questions are still open, but so there is a lot to be done. And actually, we can even consider a very general linear recurrences when, let's say, the sequence is satisfied by some there is some a polynomial operator, a polynomial in the index and in the shift operator. So that's a very general way to write a recurrence relation. And these kind of algebraic techniques can also be applied to this generalized problem. All right. So first order of business, of course, can we will solve the problem in the noiseless case, and already there well, it's not entirely trivial. What do I mean by that? So suppose that we are given any arbitrary sequence. Can we fit it to a sum of exponentials? Yeah. So that's somehow the first question. You know, when you look at some inverse problem, you want to show that it's well posed. So we have, let's say, this capital R is the number of terms. So we have two R parameters, and generically we would need 2 R measurements to have a unique solution, and that's what happens in this problem. But the question is, can we fit it to any sequence, yeah, of size 2 capital R? And it turns out that we cannot, and it's very easy to construct counterexamples. So if we don't restrict, let's say, to positive coefficients or anything like that, then there are some sets in the parameter space, in the measurement space, that cannot be fitted. So the problem doesn't have a solution, and it's relatively easy to characterize these sets, these vectors. And I will not go into too much into the details of this, but there is a very nice paper which you can look at. And I would just like to mention that the title of this paper is a Sylvester-Ramanujan system. So this kind of things were already considered by Ramanujan and Sylvester. So and as we will see in a minute, even earlier. Yeah. Okay. So existence and uniqueness we understand. Now, what about stability? So the most basic thing that one can do is to look at local stability. Yeah. So we have some parameter vector that's our ground truth that we want to recover, and we have some perturbed data. So we can define the measurement map, which maps our parameters to the measurements, and then we would like to understand the stability of the inverse. Yeah, so this is kind of standard. So we do a Taylor expansion, and then of course we have the Jacobian here. And so to first order, we need to estimate the inverse of this Jacobian. And that would give us, for small enough perturbation, that would give us some measure of stability for this problem. So when you write this down, it's a very nice exercise. So it turns out that this Jacobian can be factorized actually to a part that depends only on the nodes, on the nonlinear parameters, and to a part which is very simple, which depends only on the coefficients. And this nonlinear part is nothing but a variant of the well-known van der Monde matrix. So it's called the confluent van der Monde matrix when you basically take each column or each row of the van der Monde. Here I'm my van der Monde is the transpose of the standard van der Monde, so to say. But then you basically compute derivatives of columns with respect to the nodes, and that's this matrix. So that's kind of a very basic separation of variables that is very well known to practitioners in this field, and this not only has implications for stability but also for algorithms. So most of the algorithms basically they separate the variables and then they first recover nonlinear parameters, and then they plug back and recover the linear parameter. Yeah. So but here we already see. The big issue here in all this business is that this van der Monde matrix. So when we invert, yeah, we have the inverse of the van der Monde, of the confluent van der Monde, but basically very similar. And this means that when two nodes collide or become close, then this thing blows up. And of course, the problem becomes ill-conditioned, and that's somehow the issue that all of us have to deal with in this business. All right. So okay. So yeah. So Prony's method, a very well-known method to the first historically known method to solve this problem in the noiseless case. So that's the answer to my earlier puzzle that I presented. Yeah, so we have sum of exponentials, and the idea by Prony is to construct a polynomial. It's called the Prony polynomial, whose roots are the nodes. Yeah, and when we write down this polynomial in the monomial basis, it turns out that these coefficients in the monomial basis are exactly the linear recurrence coefficients which appear in this recurrence relation satisfied by the measurements. Okay, so the proof is one line. I mean, we can plug it here and replace the order of summation. Straightforward. So it means that so now this is the Prony's method, which is based on the earlier observation, right? So basically we are given the measurements. So first we recover the coefficients of this recurrence, and then we find roots of this polynomial. So to find the coefficients, we construct a Hankel matrix and look at the vector in the null space of this matrix. And then we plug back to the system of equations and solve it with respect to the alphas. This is a linear system, and here's our van der Monde matrix again. Okay, so that's the Prony's method, and I will talk about it later. But I mean, it turns out that for many problems, it does not have sufficient accuracy. And that's just, you can think about it, is the basic reason is that it doesn't, it may potentially not use all the available data. Yeah. Meaning that if my problem to begin with, my sequence, has more data than the unknowns, then Prony's method is not able to utilize all these additional measurements. So there is a lot of literature on extensions or generalizations, or if you will, or completely different approaches. And again, the list goes on. And I apologize if I didn't mention somebody's work here. But the basic question of stability remains. Yeah, how accurate are all these methods? Okay, so now I will be talking about the problem of super resolution, which is also known to many people. I mean, in very general context, we have it's an inverse problem. So the easiest stating would be if we have some function or object, and we observe a band limited. Let's say have some band pass filter or low pass filter, and we observe again noisy. Here I don't have noise, but these are noisy measurements of convolution of F with some filter. For example, the ideal low pass filter. And we would like to recover F. Well, of course, we have the Shannon-Nyquist theorem, which tells us if F has only low frequencies by itself, then we can recover F from G, and it gives conditions on how to sample. Yeah, so there is this band limit of the kernel, and if F itself does not have frequency components outside of this band, then we can sample with rate which is proportional to 1 over omega and recover F perfectly. And that's 1 over omega is this classical resolution limit, which is again known by many names. But the bottom line is that if F is band limited, then we can solve the problem, and I mean, not by this formula, but let's say by approximating it with FFT, etc. So, and then we have false algorithms and perfect stability because basically the Fourier transform is unitary. So, but for super resolution, we would like to go beyond that basic resolution limit, and would like to probably recover components of F which are outside of the band or smaller length scale than 1 over omega. So that's somehow general approach to super resolution, general formulation of super resolution. So now the question is, of course, what should I assume about F in order for the problem to be solvable, stably solvable? So this sparse model, so-called, is a linear combination of Dirac deltas. Yeah, it's the most non-band limited signal that you can think about. So in this talk, I'm talking only about 1D setting, but of course it can be extended, and there are very interesting problems appearing in the multidimensional setting, but I will not talk about that. All right, so that's the model, and the limited data is just the Fourier transform. So we get our sum of exponentials here. Now they are really exponentials, and the exponents are pure imaginary. So we have nodes on the unit circle, and we would like to recover the signal from this data so now we can we can start assuming additional things. For example, that our spectrum is sampled, or maybe uniformly, maybe non-uniformly, etc., etc. But for this talk, I'll just assume that I have the entire noisy spectrum in this band, and I would like to recover F from these measurements. So the noise is bounded now. We need to start making some assumptions. but this is not really. I mean, it's not substantial restriction for this problem. You can also have Gaussian noise, etc. But for the things that I will be talking about, this would be the assumption. Okay, so again, many applications of this very simple kind of toy model. I will not have time to go over these things, but again, people are. I'm sure that many of you are familiar with applications, and today I will introduce maybe a new one. Okay, so what about stability? Yeah, so we have again this Rayleigh limit, and here in this model it's very kind of simple to see that if now two spikes are closer than this Rayleigh limit, yeah, then the low resolution signal would be a convolution with the sync kernel, which would basically blur these spikes. And then the problem, of course, becomes hard if the spikes are too close. So that's how we will quantify stability. We will consider some prior information that our spikes are separated, so the minimal separation is bounded from below by some delta, which is a parameter of the model. But I mean, of course, it doesn't mean that we know where the spikes are, but we have this quantity, and then the ratio between the Rayleigh limit, the classical resolution limit, and this actual minimal separation is some number dimensioned as parameter. It's called the super resolution factor in the literature, or SRF, and the problem is hard for large values of SRF. Yeah. So again, I'm kind of skipping a lot of literature and important contributions to this problem in the well-separated case. But the bottom line would be that in this case, kind of at least in this simple setting that I'm considering, I think the problem can be considered to be more or less solved. So all these parameters can be recovered by the parametric or non-parametric methods. And then the question is, what happens when super resolution factor is large? Okay, so there is a lot of results about this, but the bottom line here is that okay, if we have capital R spikes and we have some super resolution factor which is large, then the error, the estimation error, the best possible or the worst possible error, I will define it in the next slide precisely, but that would mean that it's the error that, I mean, it cannot be beaten by any algorithm in this model. So the error is proportional to the super resolution factor. It's polynomial in the super resolution factor, but the number of spikes it's in the exponent, and that's it. And then that's the best that one can do. So it turns out that the most difficult, again, the difficult examples are when all the spikes are clustered together, and then our research is about what happens if you relax this assumption when you allow clusters of maybe of varying size, but this worst case assumption that all the spikes may be clustered together is we would like to relax it. Okay. So what is the min-max error? It's you can think about it something like this. Yeah, we are doing a uniform bound of error inferred by any algorithm, any deterministic algorithm that takes the noisy measurements and produces some estimates, and then it's uniform over all realizations of signals and of noise. So that's it. That's the standard kind of min-max error. And so cluster here again is a set of spikes which are closer than this Rayleigh limit 1 over omega. And now the important parameter is this cluster size. So we have shown that we can reduce the error from the exponent in the previous slide from capital R to this small l, and the small l is the largest, basically the largest cluster size. So yeah, so this result is about only some special case when we assume that we have only one cluster and all the rest are well separated. But it's not an essential limitation. It's just technical. So it's sufficient. There is sufficient reason to believe that this result holds also in the multi-cluster case, meaning that you can have a lot of clusters of different sizes, and then the stability of each component would be proportional, would be related to the size of the cluster of that component. Meaning that, well, in this example, we can see that the out of cluster nodes are perfectly stable. There is no blow up of the error, both the nodes and the amplitudes, while the in cluster nodes incur this blow up, this condition number. Okay, and as I mentioned, it's probably also holds in the multi-cluster case in full generality, but it's something that needs to be still shown. Okay, so how do we prove it? So now we go back to exponential analysis. Yeah, okay, so that's the local stability result that we had before. But now, how can we utilize these additional measurements? Actually, we have the entire spectrum here in this setting. Just to remind, yeah. So we have the entire spectrum. So to apply exponential analysis results, we need to subsample, and that's what we do. So we select. So we select a set of equispace samples which are well separated, and to show that there exists such a set, then that's something that needs to be shown. But I mean, it's not very difficult, but still it's something that needs to be shown, that there is basically there is a parameter which separates all the nodes in the entire signal and does not cause collisions. Yeah, because what happens is that when we plug here this lambda, so if you think about what happens with the cluster nodes, they get separated by factor of lambda, but then we can have a wraparound from non-cluster nodes which can collide with these nodes or with each other. And so the question is here to show that there is sufficiently there is at least one such parameter, the summation parameter, that it does not cause collisions, and that's somehow the main component here of this result. So we show that there exists such lambda. We take any such lambda, and then we solve the exponential fitting problem. Yeah, for this system. Yeah, for these measurements. And here we see that when we compute the Jacobian, the inverse of the Jacobian, so the van der Monde matrix here, the nodes get separated, and so we get the desired result with the correct power of the super resolution factor. Another thing here is that well, we need to make this result kind of global or semi-global, and that also can be done by a quantitative version of the inverse function theorem. I don't go too much into details here, but the bottom line here is that it can be shown that the allowed noise level is basically inversely proportional to the norm of the Jacobian, of the inverse Jacobian. And then the additional thing would be to recover the true nodes, the original nodes, from these decimated nodes. It's a kind of de-Aliasing step. and it introduces some additional complications, technical complications, but anyway, it can be shown. Yeah. So basically, we select. Yeah, we select a well-conditioned sub-problem of the full problem, and then we apply the exponential fitting stability. So that's the idea. Okay, so that's somehow the yeah, we used here in quantity inverse function theorem. It doesn't say how can we solve it in practice, yeah, with the required accuracy. So then when we look at now all kinds of algorithms, and we ask, do they attain this bound that we've shown here? Yeah, so this is a worst case bound on the stability. Well, it turns out that that in this regime, actually it's not known. Yeah, it's still open problem to devise an algorithm or to show that some existing algorithm attains these bounds, and there are some limitations. Some of them may be essential, some of them may be just artifact of the proof. I don't know, but that's the bottom line. So that's where we have our next result, which says that now we have an algorithm which is provably optimal. We call it the decimated Prony's method, which attains these bounds. And basically, it follows the recipe that I've shown in the previous slide. Yeah, we just need to select some decimation parameter. Then we apply Prony's method, which is the most simple one to do. And then we do this dealiasing step, and that's it. So now the question is, that's our next result. Can we say something about the stability of the Prony's method itself? Okay, that's the essential component of this result. Well, right now, so I'm separating here the difficulties. So given that the Prony's method is optimal, and we will see it in the next slide, then we need to solve now the super resolution problem. But our method, so it works. But the problem is that we can prove that it works only in the case of all the nodes are clustered together. So that's something that still needs to be shown. But again, this is a kind of a technical limitation. So that's it. Okay. Okay, and that's the method itself. So yeah, so we choose many lambdas. We solve the Prony's method. We solve the problem by Prony's method, and then we make some histogram, and then we find the nodes from the peaks of this histogram. And basically, our result says, okay, the sufficient density of the decimation parameters is such and such that the algorithm works. Okay, and everything is polynomial time, so everything is fine. Okay, and I mean, it runs actually it runs faster than, let's say, Esprit, and gives almost the same accuracy. Okay, so now the Prony's method. How can we prove that the Prony's method is optimal? And I think that is of interest not only to people that work in super resolution, but also to many others that may use some kind of exponential fitting or Prony's method in their research, and that's somehow now the question. Yeah, so we apply Prony's method. What do we get? Because some other methods cannot be applied all the time. I mean, in all situations. All right, so that's the Prony's method. I've rewritten it in our setting. Yeah, so now the ZJs become e to the ixj's. They are on the unit circle. Yeah, so we have this Hankel matrix. We find the kernel. We find a vector in the kernel, and we solve for the roots. All right. Okay. All right, and so now, okay, and again, in the setting of so now I replace capital R with small n. I apologize, but so that please keep that in mind. Now it's the number of nodes is this small n. Yeah, so we have perturbed data. again, and we would like to estimate the error incurred by Prony's method. Okay, so when you start when I started to kind of think about this problem, I said, okay, it should probably be easy, right? I mean, only 2 steps, 3 steps in the method, and I mean you can analyze each one. It's kind of classical, right? It's a linear system and polynomial roots. Well, it turns out that if you apply these kind of textbook methods, it doesn't give you what you want, right? So even in the simple case of a single cluster, we can show that if you apply some standard perturbation theory for linear systems, and then we estimate the accuracy of the coefficients of the polynomial, they are okay, and we check it with the measurements, with numerical experiments. But then when we solve for the roots, then things start to break down because the actual accuracy is um, is um, is better than theoretical. Yeah, so here we can see in this plot, um, so the rate that we want is the magenta line. Yeah, that's the lower rate of error blow up. It's the condition number, and so the actual errors in the coefficients of the Prony polynomial are these blue lines, so they are correct. However, when we solve for the roots, their accuracy is also the same, and that's the best. That's the best that we can get, and that we should get. However, if we now take the same rate of decay of the coefficients and then perturb the coefficients, so we don't increase the error in the coefficients, but we change them, and then we find the roots, then the roots are already off. And what it means is that there is some correlations in the errors between the roots of the polynomial, which are not taken, which cannot be taken into account by the standard classical analysis. Yeah, and so the same is for the amplitudes. If we just solve for look at the condition number and things like that, then it does not give us the accuracy that we want. So that's our result. So we did manage to make the full analysis of Prony's method, and then eventually we've shown that in this multi-cluster geometry, the accuracy of Prony's method is exactly what we expect from the min-max bounds. Okay. So there was a question in the chat. I see, what is delta? So here, small delta is like the capital delta in what was before. Yeah. So here it's just the minimal separation between the nodes. This is small delta now. Yeah. There is some abuse of notation with this delta. I apologize. Okay. Okay, so that's and actually this result we can think about it as also an extension of the previous result about min-max bounds, but only in the case, of course, that our bandwidth is constant, meaning that basically we don't have these extra measurements that we expect from the full super resolution problem. Okay, but it's already a generalization to the multi-cluster setting. All right. So I don't, how much time do I have?
About 10 more minutes, 15 more
10
minutes.
more minutes. Okay, okay. So I'll skip the details, but I'll just say that basically the proof is we compute this difference between the polynomials symbolically, and then we are able to apply standard tools from complex analysis like Rouché's theorem, but we know what are the perturbation polynomials. And so these correlations between the errors are taken care of in this analysis. And this analysis is not unique to super resolution problem. It's entirely symbolic computation. We only plug in the specific assumptions that the nodes on the unit circle, for example, only at the very end. So I hope that parts of this can be used only also for some other applications of the Pronis method. All right. So yeah. So and for the amplitudes recovery, we also have some key observations which basically take into account the some correlations between the errors also in this linear system, and we are able to show the full result in this way. Yeah, and we also, as a nice corollary, we also show that actually the Pronis method itself is, if you look at it from the perspective of backward error, it is stable. Yeah, provided that you use stable algorithms for root detection and for linear system solving, then the entire method itself is also backward stable. Okay, so that's about that, and and now I come to the last part of the talk. So this is the application of exponential analysis to reaction diffusion equations. This is joint work with Rami Katz and Giulia Giordano. They are at the University of Trent, and Rami Katz will be joining Tel Aviv University next year. Okay. So reaction diffusion equations. This is I admit that this is not my field, and everything is related to to control and optimal control and observability and applications. It's my collaborators. I don't know much about that. But okay. But the problem is, as I understand it, it's so we have some reaction diffusion system, and we would like to recover I mean, okay, in the general case, we would like to control maybe the system which is governed by this equation, to have some control, or in our case, to just to recover the parameters governing this equation. And the existing methods, they have some unrealistic assumptions. For example, they need to know the entire operator, or its full sequence of eigenvalues, or they need some continuous measurement of the state of the solution of the equation. And so that's somehow can be considered an open problem, yeah, to get a constructive method for identification of such systems. Okay, so mathematically, what we have, so this is the kind of the simple linear equation. So we have P and Q are known functions. The solution, yeah, so these subscript are derivatives, of course, partial derivatives. So it's 1D on an interval with Dirichlet boundary conditions, and we have eigen system of this spatial operator, psi n and lambda n, yes. And so we can write the solution as an infinite series, and we observe what is our data. We observe some convolution called non-local measurements, convolution of the solution with some convolution kernel. Okay, which when you plug this in, you get a series which looks like this. So it's kind of an infinite exponential sum. And these exponents are, of course, exponentially, or in this case, super exponentially decaying. Yeah, and we would like to, in the first step, we would like to recover some of those exponents from these measurements. Yeah, so we fix some number n1. And now we have to, again, to make some additional assumptions so that the whole thing works. But these assumptions, we believe, are realistic. So this C, this convolution kernel, we assume that it's approximately band limited, so meaning that it only has some capital N1 non-zero coefficients, and then the coefficients somehow decay. And then we are able to apply exponential fitting. But now it's a very interesting thing happens that we have our perturbation term is not arbitrary as it was before, but it itself has a structure of the sum of exponentials. So just to make analysis simple, we have this epsilon here, yeah. So it's basically now depends on single. So the perturbation is only one-dimensional, but this can be generalized to decaying series, etc. And then this is a much work in progress, but what we are able already to show is something about the conditioning of this problem. Yeah, again using tools of that I mentioned earlier. So we define condition numbers, and then we look what happens, and we look what happens with these condition numbers as we change as we play with the parameters of the problem. So here, notice that again, it's very different from super resolution. It's decaying real exponentials, and in this case, they are actually decaying with the order of n squared. So very interesting. So we have two regimes for this problem. One regime is when we take delta. This capital delta is the step size. Yeah. So here we sample our solution at discrete points of step size delta, capital delta, and then we take this to infinity, meaning that we go further and further into the measurements. And it turns out that actually the condition numbers decay exponentially with this parameter. Yeah, both for the eigenvalues and for the linear coefficients. And another regime is actually when we take the number of exponents to infinity, this n1 parameter to infinity, and in this case the condition number is even better. It's super exponential in this parameter. Okay, so the problem becomes super exponentially stable in this regime. And I mean, this thing works, yeah. So we apply let's say esprit, Prony's method to this problem, and we see that up to some level, of course, which is defined by numerical precision, we are able to recover the eigenvalues and in some cases the PDE itself. So that's yeah. So this is, you see the super exponential decay, which is very nice. So I mean, it's for me it was a complete surprise that in this very hard setting, kind of simple methods like exponential fitting would work, but they work. Okay, so I'll skip that and thank you. I think I'm done with the main part of the presentation. So now I'll be happy to take questions.